What we're going to do in this video is we're going to review some basic concepts of a graph so that when you get to your homework, you are not confused or feeling lost or trying to recall information from a previous course. So the first thing that we're going to talk about is specifying y-coordinates as an exact expression and as a calculator approximation. So when we put values into a function, we can get exact values out. We can also get a calculator approximation when those numbers look a little bit more complex, a little bit more less than basic. For instance, square roots or fractions. Now, when we approximate our values, we're going to approximate them to 3 decimal places. So we're always going to do that. We're going to start practicing that with this lesson, going out 3 decimal places, which is the nearest thousand. After we look at the y-coordinates of given equations and their graphical representation, we're going to use the vertical line test, which you might have used in Algebra 1, possibly in Algebra 2. So we'll recall that for you. And then also we're going to determine the domain and range of a graph, which I know that we've worked on in this course, but we are also going to look at it not given the equation, but its graphical representation. So those are the 3 things that we're going to do. So the first one is this graph f of x equals the square root of x. This is one of our parent functions. So when we graph this parent function, we know looking at this equation right here, let me get that off the screen. Looking at this equation, f of x equals the square root of x. When we graph this using our parent functions, we put a 0 in. The square root of 0 is 0. We know that we cannot put any negative values in for x, otherwise we'll have a square root of a negative. Then we put a 1 in, so we put 0 in, we get a 0 out. We put a 1 into the function, the square root of 1 is 1. Then we put a 2 in, and we say, we can't do that without a calculator. So we go to 3, and we say, we can't do that without a calculator. And then we go to 4, and we try and graph as much of this picture that we can without using a calculator. Well, the fact of the matter is that you can put a 2 in for x, and we know that. So when we put a 2 in for x, we're going to, let me change this to my pen. When we put a 2 in for x, we're calculating f of 2. So we've got the square root instead of the square root of x, we've got the square root of 2. This can be written as an ordered pair. Our ordered pair would have an input of 2 and an output of the square root of 2. This square root of 2 is our exact value. So this is our exact value for the function when you put a 2 in for x. And notice how I'm using the color yellow. We come back here, an exact expression is going to use the yellow highlighter, and there's our square root of 2. We also can show this as an approximation because not all of us know the value of the square root of 2. So if we put this into our calculator, and I'll let you put that into your calculator right now. So what I would do is I would hit pause on the video, take out your calculator, and calculate the square root of 2. When you're ready to check your answer, press play. So what you should have found is that the square root of 2 is approximately 1.414. These two ordered pairs represent the same point on the graph. However, one is an exact value and the other is an approximation. This is an approximate value. And that location would be right to up about 1.4 units, which you can see falls right on our graph of the square root function. Coming over here, we have f of x equals x cubed. We know this function very well. This is a cubic function. And what we do is we put a 2 in, we get an 8 out, a 1 in, we get a 1 out, 0, 0, -1, -1, -2, -8. Well, here we want to put in the negative square root of 2. So I'm going to calculate f of negative square root of 2, which means I'm going to take a negative square root of 2 and I'm going to multiply it by itself 3 times. When I multiply the negative by itself 3 times, I get a negative, and the square root of 2 times the square root of 2 times the square root of 2 is 2 times the square root of 2. So when I put a negative square root of 2 in, which is about negative 1.4 from the last problem, I'm going to get negative 2 times the square root of 2, which is negative 2 times 1.4-ish, which would be about negative 2.8. We put this into our calculator because they want an exact value. So our ordered pair would look like the negative square root of 2. And our y value is negative 2 square root of 2. Again, I'm going to use a yellow highlighter to show you that that's the exact value. So this is the exact y value. And the approximate y value go ahead and press pause, and when you're ready to check your answer, you can hit play. And that approximate answer is negative 2.828. Okay, the vertical line test allows us to check to see if a graph is a function. So remember how we defined a function. The definition of a function, every input, which means every value of the domain, every member of the domain has exactly one output. Excuse my writing. Which means when I put a value in for my function, which are members of the domain, so when I put a value in, I'm only going to get one output. I can use the vertical line test to test to make sure that I only have one output for every member of the domain. So we look at this sinusoidal curve, which you know from Algebra 2 and also from our parent functions. As I pass the vertical line through this sinusoidal curve, it only intersects the curve in at most one point. So there's absolutely no places from left to right where I would pass through the curve and have two intersection points with this vertical line. That makes it a function. So that just gives you a visual representation that you only have one output for every input. Whereas on this circle, you can see that maybe you can see just looking at it, not even using the vertical line test, when I put a value of 1 in, -1 in this case, when I put a value of -1 in, I get 2 different outputs. That's not functioning. That's like the Coke machine that you put the 50 cents in, or 75 cents, or $1, or if you're watching this video in 2022, it might be $1.50. But when you put that money into the Coke machine and you get 2 different sodas, the Coke machine isn't functioning. It doesn't function. That's what's happening here. We have 2 different outputs for a single input. Therefore, it's failing the vertical line test. This fails the vertical line test. Now, you may have known this, but hopefully just watching this, maybe you see it in a different way, and it'll help you do your homework a little bit better. Now, the last piece that we want to talk about is the domain and range of a given graph. So here we've got this graphical representation. We've got a beginning and an end. That beginning and the end means that our domain, I'm going to try and do this a little bit nicer here. Our domain, we'll try a highlighter. We'll say our domain is yellow. So our domain goes from -infinity to +infinity. -infinity to +infinity. If I try and put, let's say, -4 into the function, there are absolutely no outputs. So -4 is not a member of the domain. Neither is -5, -6, -7. There is not one negative value that will give me an output for this graph. The very first value that I can put in is a +1. When I put a +1 in, I get a closed circle on the graph. When I put a 2 in, I get a value that's a little bit bigger than 2 as an output. Every value in between 1 and 2 has an output. Every value through 3 has an output. As a matter of fact, every value through 5 has an output on this graph. Therefore, our domain goes from -1 to 5, and it is a closed interval. So our domain goes from +1 to 5. +1 to 5. I think I said -1 back there, but I'm not going to redo the entire video over that. You probably knew what I was talking about. You're getting too used to me. You put a 1 in and we get an output. Every value up through 5, we get an output. Therefore, our domain goes from 1 to 5. And what are these called? Brackets, which signify a closed interval. Now, if we had an open circle on one of our endpoints, we would have parentheses on one of the ends. If we had open circles on both endpoints, we would have parentheses on both ends, and it would be an open interval. Now, our range sometimes is a little bit harder to see, and that's only because it's vertical. But we're going to treat it the same way. If you need to tilt your head to the side, go ahead and tilt your head to the side. Our outputs, that was kind of a joke. You can tilt your head like my dog tilts his or her head when I'm talking to them. As a matter of fact, he's doing it right now. Anyway, back to the range of the function. Tilting my head and kind of looking at this as I did the horizontal axis, I've got -infinity and down at the bottom of the graph, and I have +infinity towards the top of the graph. Now, there aren't any negative outputs. So none of these negative values are included in my range. A matter of fact, there aren't any outputs until I get to a y value of 2. And then from that y value of 2, my outputs are continuous. They don't stop. There's no break until I get to the highest point of the graph, which is a value of 4. So my range is also a closed interval from 2 to 4. Okay, let's try a little bit more challenging graph. This graph has closed circles on these 3 ends and an open circle at the ordered pair 3, 2. So again, I'm going to highlight my horizontal axis. I'm looking for my domain, which goes from negative infinity to positive infinity. I'm going to start ruling out values that are not part of the domain. So going from negative infinity to positive infinity, I need to rule out values that are not part of the domain. Putting in these values where x is negative 6, negative 8, negative 9, negative 10, they don't produce any outputs onto the graph. The very first input that produces an output is negative 4. And then you can see negative 3 produces an output, and every value between negative 4 and negative 3, every value until we get to positive 3. But even at positive 3, where I think there's an open circle, there's a closed circle. So even positive 3 has an output. So this domain goes from negative 4. I thought that it stopped at 3, but there is an output when I put a 3 in. When I put a 3 in, I get a 4 out, and that's this point right here. Then there's positive 4. Every value between 3 and 4 works until I get to 5. And that's where my domain ends. So the domain for this function is negative 4 to positive 5 with brackets. The range is super cool, totally fun. We'll use a blue marker here. My range values, remember, negative infinity to the bottom, positive infinity on top, and now I'm going to take out all those values that are not included as outputs. So none of these values, negative 4 doesn't have an output. There's no output at negative 4. There's no output of, I should have said of negative 4. There's no output of negative 3. There is an output of negative 2, and it is a closed circle, which means negative 2 is part of the range. And then there's an output from negative 2 all the way to positive 2. So from negative 2 to positive 2, as this segment increases, I get to an output of 2 that is not included. So my range starts at negative 2 with a bracket because negative 2 is a definite output, and it goes to positive 2, but it does not include positive 2, so that's a parenthesis. Now there's another portion of the domain that starts at y equals 4, and it goes as high as y equals 5. And those are brackets. So our range has 2 intervals, negative 2 to positive 2, and 4 to 5. The brackets and the parentheses are very, very important here. So you'll have a few of these problems in your homework. I'm going to move the domain and range over here to the right so that now we can evaluate h of negative 2, h of 3, and the absolute value of h of negative 4. H of negative 2 means put a negative 2 into the function and look for our output, which is negative 1. H of 3 means put a 3 into the function. When we put a 3 in, our output, which we already discussed, is 4. So h of 3 is equal to 4. And then the absolute value of h of negative 4, I'm going to keep the absolute value there, and I'm going to first figure out h of negative 4. I put a negative 4 in, and I get a negative 2 out. So I have the absolute value of negative 2, which is positive 2. So what we're saying is negative 2, negative 1 should be an ordered pair on the graph, which it is. 3, 4 should be an ordered pair on the graph, which it is. And then negative 4, negative 2 is an ordered pair on the graph, but they want us to take that output and make it positive, which is what these absolute value bars stand for. And now you should be able to do at least the first half of your homework without too much confusion or frustration.